Hello everyone. So in today's video, we're going to be continuing to talk about the chain rule. And specifically, we're going to be doing a little bit more practice, just general practice with how the chain rule works. And then we're also going to see how we can use the chain rule to actually prove a new derivative rule. So remember that we know how to take the derivative of e to the x, but we have not yet learned how to take the derivative of a different number to the x, like 3 to the x, or 5 to the x, or 1/2 to the x. And so today we'll learn that rule, and we'll see that the chain rule is what allows us to actually prove that derivative rule. So first, let me just write down again what the chain rule actually says so that we can refer to it as we do some examples. So the chain rule says that if you have a function h of x, that can be written as a composition of f of g of x. So that means that we have an outer function f and an inner function g, and the g of x is kind of being plugged into f of x, or f of u is what we're calling it in this case. So if you have a composite function, then last time we saw that the derivative of that composite function is going to be equal to the derivative of the outside function, leaving the inside function as its input, and then you multiply that by the derivative of the inside function. So we'll do a couple of examples of that in a moment, actually right now. So the first example I wanted to do was actually going back to yesterday's video. So we talked about these two functions. We talked about how to break these up. H of x is equal to sine of x squared, and then also h of x is equal to sine squared of x. So we went over what the inner and outer functions were for these, but we didn't actually find what the derivatives were. So I asked you to do these on the worksheet from last time, so hopefully you did them there, but I just wanted to go over them because especially sine squared of x is one that I've just seen a lot of students have some difficulty with. Okay, so what is our outside function in this case? Well, just literally what's on the outside is the sine part, right? So our outside function is going to be f of u is equal to sine of u. And then what's our inside function? It's g of x is equal to x squared. So in order to apply the chain rule, we want to first of all, take the derivative of the outer function. And we're going to start doing it just with that u there as kind of a placeholder. So the reason that we're using u instead of x as our input for the outer function f is that I just think it kind of makes a better placeholder because we're eventually going to replace u with x squared. And it just feels like a little bit less confusing to me to replace u with x squared than to replace x with x squared. If you're using x's for everything, there's just a lot of x's floating around. Okay, so what's the derivative of sine of u? It's cosine of u. But we don't want just f prime of u, we need to put it back in terms of x. So we're going to do f prime of g of x. So we're going to put our original inside function back in. And so we're going to get cosine of x squared. So as I mentioned last time, the way that I like to think about it is you're basically just kind of taking the derivative of the outside part and you're just kind of leaving the input as it is. You're not changing the input, you're just kind of doing stuff around it, right? You're doing the derivative of the outside part while leaving that part alone. And then the other thing we need is we need the derivative of the inside function, which is x squared, so the derivative is 2x. And so putting these together, the derivative of h of x is going to be the outside derivative, so that was this part, cosine of x squared, times the inside derivative, 2x. So maybe a slightly nicer way of writing this would be 2x times cosine of x squared. People tend to write, if you're multiplying a trig function with like x or x squared or something like that, people tend to put it first just so that it doesn't get kind of mixed up with the input. Because sometimes people don't put parentheses, right, with trig functions. So just to be really clear, it's kind of nicer to put that other part in the front instead of next to the x squared. Okay, so let's do this other one, which, like I said, I think is a little trickier. So in this case, I think a better way to write this in order to really see what the inside and outside function are is sine of x squared. So we talked about this last time. It's just a notational thing that we write sine squared of x instead of sine of x squared. So in this case, the outer function, well, what's on the outside here? It's the squaring part. So the outer function is going to be u squared, because like the original, or the function over here, we were doing sine of something, right? So sine was kind of the outside thing that's happening. In this case, we're doing something squared. So we want our outside function to be the squaring function. And then the inside function is going to, in this case, be sine of x. Okay, so again, we want to take the derivative of the outside function. So what's the derivative of u squared? Well, it's just 2 times u. But then we want to go and put our original input back in. I think this is where I think this is the part of this one that makes it maybe a little bit confusing. So what are we going to do? Instead of putting a u here, we're going to put back in our original g of x. And what was g of x? It was sine of x. So again, just to go back to this idea of like kind of visually what's going on here, the way I would think about this is, so you might think like if you're taking the derivative of something like, I'll just say u squared, the way you might visualize it, which is what I do, I kind of picture that 2 like literally coming down. Like I picture like this 2 is going to go here and become 2u, right? And so similarly, I just picture that same thing happening here, right? The square is coming down and it's becoming 2 sine of x. So same way that the power rule always works, it's doing that same thing. It's just that instead of it being x or u or w or whatever, it's sine of x. So our outside derivative is 2 times sine of x. And then our inside derivative in this case is the derivative of sine of x. So what's the derivative of sine of x? It's cosine of x. And so we're going to multiply these two things together to get our final answer. So it's 2 times sine of x times cosine of x, which you might remember is actually the double angle formula for sine. So this is the same thing. Hopefully I'm remembering this right. I believe that's the same as sine of 2x. But you don't have to simplify it that way. I just wanted to point that out. So here's our first derivative, here's our second one. Okay, so let's do some more examples. And I would encourage you on these next, we're going to do just 2 more examples. And I would encourage you to pause the video and try these yourself, and then we'll go over them together. So 2 examples I want to do. The first one is h of x is equal to, where is it? Tangent of 3e to the x. And then the other one I want to do is h of x is equal to e to the 5x. Okay, so like we did on the other ones, I'm going to still write out what's the outer and the inner function. As I mentioned in the last video, I think when you're first starting out, literally writing down, all of this stuff can be really helpful. Sorry, it's for some reason not scrolling. There we go. Writing down all of this stuff can be really helpful, but I think eventually you're going to want to get to the point where you don't have to write all of it down, just because, especially when we're going to be blending the chain rule with other rules, there will just be too many different functions floating around for you to really name everything. Oh, that's f of x, that's g of x, that's, you're going to run out of functions. So yeah, I'll write it out that way, but then I'll also kind of just talk through how I would do it without writing any of this stuff down. So in this case, the outer function is tangent of u, right? Because we're taking tangent of something. And the inner function is 3 times e to the x. So what is the outer derivative? Well, f prime of u, the derivative of tangent is secant squared. And then we want to replace u with the original input. So we're going to have secant squared of 3e to the x. Oops. Okay, and then what's the derivative of the inside part? Well, the derivative of e to the x is just e to the x, and then we're multiplying it by 3, so that 3 gets carried along. So we get 3e to the x. And so our final answer here is we're going to multiply together this and this. So we get h prime of x is equal to secant squared of 3e to the x times 3e to the x. Which, just to be kind of consistent with what I did on that other one, I would personally probably rewrite this as 3e to the x times secant squared of 3e to the x. So how would I kind of think about this without having to write all this stuff down? Well, I would just think about, again, you're kind of taking the outside derivative. So you're taking the derivative of this part, and you're leaving the inside alone, right? So that's how you end up with secant squared of 3x. That's kind of taking the derivative of the outside part and leaving the inside part alone. And then you're just multiplying it with the derivative of the inside function. So you look at the inside function, you find the derivative of that, and you just multiply with that. And so that's where this part comes from. Okay, so I did this next example for a specific reason. This type of function is going to come up a little later, so that's why I picked this one. So in this case, the outer function is e to the u, right? If you have e to any power, the outer function is always just going to be e to the u. And then the inner function is going to be whatever that exponent is. So in this case, it's 5 times x. And so our outer derivative is going to be still e to the u, right? That's what the derivative of e to the x is. So the derivative of e to the u is just e to the u. But now we're going to put back in our original input. So we're going to get e to the, our original input was 5x, so we have 5x. So again, I mentioned this last time, but anytime you're doing a chain rule problem involving e to a power, whatever your original function is will always appear as part of your answer, and then you'll be multiplying it by the derivative of the exponent. So the derivative of the inside function in this case is just 5. So altogether, our derivative is going to be e to the 5x times 5. So h prime of x is equal to e to the 5x times 5, which you might want to rewrite as 5e to the 5x. So one thing I just want to quickly point out, and these are actually not necessarily the best examples for that, so I want to actually scroll back to these for a second. I just thought of kind of a common mistake that I just want to make sure I mention. The most common way I see people mess up on the chain rule is that they'll kind of simultaneously take the derivative of the outside and the inside part. So for example, looking at this one, an incorrect way to do this would be to say, oh, the derivative is cosine of 2x. You can't kind of take the derivative of both parts at once. You always want to, and that's why I've been trying to talk about kind of leaving the inside part alone and just doing stuff around the outside first. So whatever your original input is going to stay as it is, and then you're not taking the derivative of that part until after. So I just want to quickly mention that because that's kind of the most common way I see people do this wrong. All right, so I want to show you one other kind of like special case for the chain rule. So basically, there are certain cases where the chain rule kind of doesn't, comes out simpler than it has in a lot of these other examples. And so I just wanted to show you a few examples of that. So let's look at one example to start with. So let's say that our function is h of x is equal to sine of x minus 1. So in this case, the outer function, And I guess I should switch up my colors again. So the outer function in this case is sine of u. And the inner function is x minus 1. So the outer derivative is going to be cosine of u, and then we can replace that with x minus 1. So we get cosine of x minus 1. And then the derivative of the inside function, well, the derivative of x minus 1 is just equal to 1. So when we go and multiply those together to give us our final answer, we're going to get cosine of x minus 1 times 1, which is just equal to cosine of x minus 1. So in situations like this where the inside function is just x plus or minus a number, or just x, well, if it's just x itself, then you don't have to even use the chain rule. But if it's just x plus or minus a number, then there's like not really an inside derivative, right? It just ends up being taking the derivative of the outside. And I wanted to just kind of show you like why that might be, or like how you can think about why that is. So I just want to pull up quickly a graph in Desmos. So we talked about in the last video how if you have sine of x and then let's say you do sine of 2x, the graph of sine of 2x has a different shape, right? It becomes a lot steeper, or it comes twice as steep exactly, because it's been compressed by 2 horizontally. And so what that ended up meaning is that the derivative of sine of 2x ended up being 2 times cosine of 2x. And that's because the derivative of the inside function was 2. And how can we make sense of that visually? Well, it's because the graph of sine of 2x is twice as steep at its very steepest than the graph of sine of x. And so that means that the derivative, if it was just cosine of 2x, it wouldn't go high and low enough. It needs to reach heights of 2 and negative 2 in order to really capture the steepness that you get on the graph of sine of 2x. And let me make this a little bolder. Sorry, I know this is a lot to look at right now. So, however, let's say instead you are comparing sine of x and sine of x minus 1. So sine of x minus 1. So notice that the shape of sine of x minus 1 is not different. All that's happened is that it's been shifted horizontally. And so if you have a graph and all you do is you pick it up and you move it over, you're not going to change the shape of the graph. You're not going to change its very steepest part or its very least steep part. It's going to have those exact same kind of pattern of steepness. It's just that all of those parts have been kind of shifted in one direction. And so that means that, so the derivative of sine of x is cosine of x, right? So this is the function, so cosine is in red and sine is in blue. Cosine is the function that captures all of those different slopes in sine of x. And so similarly, if you have sine of x minus 1, so here's sine of x, oops, sorry, I'm having trouble getting these to go on. Here's sine of x minus 1. So similarly, the derivative of sine of x minus 1 should be cosine of x minus 1. Because it's still like, it's never getting steeper than 1 or negative 1. So it should still kind of have that same shape. It's just that it's been shifted over compared to the original derivative. So I guess what I'm trying to say here is that when you have a composite function where the inner function is just basically a horizontal shift of x, then your derivative, if you use the chain rule, isn't going to really be multiplied by anything. It's just going to be multiplied by 1. And I just wanted to kind of explain why that is. So it's because when you do something like sine of 2x, you're fundamentally changing the shape of the graph. Whereas if you do something like x minus 1, you're not fundamentally changing the shape of the graph. So let me just kind of summarize that here. So if h of x is a composite function with an inner function g of x is equal to, I'll just say x plus a. So you're just adding, a could be a positive or a negative number, right? You're just adding or subtracting some number. Then basically h prime of x is just going to equal to f prime of g of x. Like you're not going to, because the derivative of g of x is just 1, you're not going to have that g prime of x part. And the reason I'm bringing this up is because I think it's just nice to like be able to recognize these right away. So another example would be if you have the function h of x is equal to e to the x minus 5. So what's the derivative of this going to be? It's just going to be e to the x minus 5. Because you take the derivative of the outside function, leaving the original input as it is, and then there's no derivative of the input derivative is just 1, so it's not going to affect the derivative. Another example would be if you have the composite function square root of x minus 3. So the derivative, and another way of writing this would be 1/2, or sorry, I'm getting ahead of myself. Another way of writing this would be x minus 3 to the 1/2, right? So what's the derivative of this going to be? It's just going to be 1/2 x minus 3 to the negative 1/2. So it's just going to be 1/2 square root of x minus 3. So I just wanted to bring these up so that when you see them, you can recognize them and recognize that it's a little less work. You can just kind of do the derivative of the outside function, and that's really all you have to do. Okay, so last thing I want to talk about is taking the derivative of a to the x. So basically exponential functions where the base is any number, not necessarily e. So the derivative of f of x is equal to a to the x. So I'll just say what the rule is first, and we'll see an example, and then after that I'll go through the proof, which, like I said, uses the chain rule. Okay, so the derivative of a to the x, so just like e to the x, a to the x is part of your answer. But it's not just a to the x, it also gets multiplied with ln of a. So an example of that would be, let's say if you're trying to take the derivative of 3 to the x, the derivative of 3 to the x would be 3 to the x times ln of 3. So one thing I just want to make sure is really clear is, what is this ln of 3? What is that? Is it a function? Is it a number? It's just a number, right? ln of any number is just the number that you would need to take e and raise it to get the number inside the parentheses. So ln of 3, if you type it into a calculator, I'll just do it right now. Should be a little bit more than 1. Let's see. Sorry, I didn't do this ahead of time. But ln of 3 is equal to approximately 1.0986. So just a little bit more. It's like 1.1. So my point here is that when you're taking this derivative, don't get thrown off by this ln of 3. It's just a number. It's basically just saying that the derivative of 3 to the x is not exactly equal to 3 to the x. It's close. It's kind of off by a certain factor. In this case, a factor of about 1.1. Okay, so we're going to prove this using the chain rule, as I mentioned. So proof of the derivative of a to the x is equal to a to the x times ln of a. So a few things that we're going to be using in this. So one is the chain rule. And we'll see how that comes up. And then there's a couple of other facts I just want to quickly mention that you may kind of forget from pre-calculus. So one of them is that if you have any number, let's just say w is equal to e to the ln of w. So why is that? Well, what does ln of w mean? ln of any number, by definition, basically any logarithm is asking you to find an exponent, right? It's asking you to find the exponent that you can raise a number to get this number. And in the case of ln, that base is e, right? ln is log base e. So ln of w is literally the number you would need to raise e to in order to get w. I know that's kind of a confusing sentence, but like maybe just give like a quick side example. Let's say you took log base 2 of 8. That's equal to 3, right? Because log base 2 is asking you what power would you have to take 2 and raise it to get 8. That's how logarithms work. They're asking you to kind of figure out how to go from this number to this number using exponents. And so in the case of ln is a log with a base of e. So ln of w is the number you would need to take e to in order to get w. So looking at this expression, we are taking ln of w and then we're taking e and raising it to ln of w. So we're taking e and we're raising it to the number you need to raise e to get w. So of course that's going to be equal to w. It's just kind of by definition. And I think this is one of those things that is, you kind of just have to stare at yourself and convince yourself, because it sounds more confusing than it is when I try to explain it out loud. So if you don't really get that, sit down and then try to convince yourself that it's true. And it might come down to re-teaching yourself what the deal is with logarithms. And that's another thing that, we don't really have time to do like a big review about logarithms. So that's something that comes up on the pre-calculus review that I post on Canvas. You're always welcome to drop in and look at those questions and see, that might give you a good idea of like things you might need to review as it relates to logarithms. Another fact we're going to use is a logarithm rule, which says that if you're taking any kind of a logarithm of a number to a power, that's the same thing as bringing that exponent down and just multiplying it with the logarithm. So that's it's sometimes referred to as a logarithm law. So it's a law of logarithms. And then one more fact that we just saw earlier is that if you take the derivative of e to the some number times x, so I'll just say wx. So we did an example earlier on the first page. We took the derivative of e to the 5x and we just got 5e to the 5x. So basically if you have e to just a number times x, you're going to get e to the x, and then you'll have to multiply that with whatever that constant is, because that's the derivative of 5x. So in general, the derivative of e to the wx, if w is a number, or I'll just say a constant, maybe let's call it c, because there's another w floating around. So that's just going to be equal to ce to the cx. Okay, so let's get started now on the actual proof. So we're going to start by kind of rewriting a to the x a different way. So a to the x can also be written as e to the ln of a to the x. So where did that come from? That's just this second rule that we have written down, and instead of w, we're using a to the x. So a to the x can also be written as e to the ln of a to the x. So this is coming from fact number 2. And then using fact number 3, well, let's forget about this e for a second and just focus on this. So ln of a to the x, we can use the power rule and we can bring that x down. So we can rewrite this as e to the ln, or sorry, to the x times ln of a. And that's using fact number 3. So now let's actually take the derivative. So the derivative of a to the x, according to what we just came up with here, should be the same as the derivative of e to the x ln of a. Right? Because e to the x ln of a, according to what we just did, is another way of writing a to the x. And it looks a lot more complicated, but the advantage of it is that we actually know, I just told you how to take the derivative of a to the x, but pretend you didn't know that yet. If you didn't yet know how to take the derivative of a to the x, you do know how to take the derivative of this thing. So it looks complicated, but remember, ln of a is just a number. So this is like, imagine this is e to the 5x or e to the 3x or e to the 1.2x. It's just e to x times a number. And so using the chain rule, we know that, and I guess I didn't really have to write down the chain rule as its own fact, because really, maybe I'll just do this. The chain rule is really just informing number 4. So the derivative of e to the x times ln of a is just going to be ln of a. Actually, let me write it in the other order. It's just going to be e to the x ln of a times ln of a. So again, where did that come from? It's just this fact at the bottom. We have ln of a is a constant, right? This is a constant. It's just a number. And we know that if you take the derivative of e to the x times a constant, the derivative is just going to be, because of the chain rule, it's just going to be e to the x times that constant times the constant. Okay, so now let's actually rewrite this, and we're basically going to use the same thing that we did to kind of go from this to this. We're going to use it in the opposite direction. So we have e to the x times ln of a. Well, that's the same thing as e to the ln of a to the x. And maybe let me just write down here, this was fact 4. So here we're using fact 3 again, just kind of cleaning things back up. And then we still have this times ln of a. And then we can use fact 2 again. So fact 2 was the one that said that you can, this funny business, that you can rewrite a number as e to the ln of that number. And so we're just going to kind of go back. So now we have e to the ln of a to the x, and so we can rewrite that as just being a to the x times ln of a. And so that used fact 2. And that's it. We know that that's what I told you at the beginning was the derivative, and now we just showed using the chain rule that that is in fact the derivative. So just to be really clear, I like to always mention this after I do a proof, just because I've in the past had students get confused about sort of what the point of the proof is. The proof was just to sort of show you why this rule works the way it does. You don't need to ever repeat this process. In order to take the derivative of a to the x, you're allowed to just use this fact. So this, from here on out, you can add this to your list of derivatives that you know. You don't need to go through this whole process again. This whole process was just to show you where that derivative actually comes from. So let's do one more example, kind of putting together this new derivative rule with some of the stuff we were talking about earlier. So let's find the derivative of let's call it h of x is equal to 3 to the x squared plus 1. So this is a composite function, right? Because it's not just 3 to the x, it's 3 to some other function. And so in this case, our outside function would be 3 to the u, and our inside function would be x squared plus 1. So what's the derivative of the outside function? Well, we just learned that the derivative of a to the x is a to the x times ln of a. So the derivative of 3 to the u is going to be 3 to the u times ln of 3. And actually, maybe we even did this one. Yeah, we did this one up here, basically. Okay, and so now we're going to put back in our original inside function. So we're going to get 3 to the x squared plus 1 times ln of 3. And we're not plugging anything different into ln of 3 because ln of 3 is just a number, right? There's no variable in there to plug anything into. And then the derivative of the inside function is going to be just 2x. So what is our overall derivative going to be? Well, we're going to put together this piece and this piece, and we're going to say h prime of x is equal to 3 to the x squared plus 1 times ln of 3 times 2x. And, maybe you could write it a slightly different way. I would probably order it like this. I would probably say ln of 3, 2x, 3 to the x squared plus 1. But it doesn't really matter. Just as long, the main thing I just want you to realize whenever you're doing these is just remember that ln of 3 is a number. So for example, if you had to take like a second derivative here, and we'll talk tomorrow about how to do derivatives that involve both the product and the chain rule. But if you had to take the second derivative here, you would just treat ln of 3 as a number. You would just kind of let it kind of float along with the derivative the same way that you do if it was like 5 or some other number. All right, so that is it for this video.